Hello class, welcome to chapter 11 where we're going to talk about polymorphism. Looking at your syllabus and schedule, we see that we're right on track. We're here in October looking at arrays and polymorphism. Next week will be your midterm exam. You should be able to see that information on Blackboard this week also. Okay, looking at chapter 11. I wanted to take a look at the PowerPoint. It has a very good PowerPoint presentation for this chapter, and this is the PowerPoint that's available to you on Blackboard. If you'd like to take a look, I want to show you how there are some links and things in here. You have so many resources available to you this semester. I understand if you've already found other resources, but please be sure you're watching videos that are available and looking at all of the different options you have for learning the material. In Chapter 11, we're talking about inheritance and polymorphism. We've already talked about how classes are so important in defining objects, and your Revell content did a great job with all of the videos you had available in explaining about how you would design classes and decide what kind of variables and properties are necessary for your classes. In this chapter, we want to talk a little bit about some more advanced concepts, and this is some of the powerful features of using object-oriented programming, the ability to reuse our code and reuse our class definitions and all of the methods associated with those classes. So, in our example, you want to define classes to model circles, rectangles, and triangles. Because these shapes have many common features, so what's the best way to design these classes so that you don't have to redundantly code each one individually? The answer is to use inheritance. In this chapter, there are a lot of objectives talking about superclasses, how to interface with the superclass constructors and methods. We'll look at all of these different kinds of things. Now, when we're talking about classes, you all have done a great job with your UML diagrams, and you know that, for example, if we wanted to define a class that defined a geometric object, we might have data variables like the color, whether it's filled or not, and what date it was created. We could then have methods associated with our object, like the constructor of the object itself, a constructor that allows the data to be passed in, like the color and whether or not this object should be filled. We could have a method that allowed us to get the color of our object and return it to our caller. We could have a method that allowed the caller to set the color. We could have a method that returned a Boolean value indicating whether or not this object is filled. Then we could have a setter that indicated or allowed, our user to set that Boolean value as to whether they wanted this object filled or not. We could again have a method that returns the date this object was created. And then finally, we're going to show you how to override the system's toString method to return a string representation of an object. Now, our generic object here in our UML diagram has some children. It has some subclasses. In our example here, our geometric object class is our superclass, and the circle and the rectangle are subclasses. We could also think of this as parents and children. Each of these classes of shapes inherits characteristics from the parent, but each of these children add their own characteristics as well. So if we look at the circle, it adds a data value of the radius. It adds a couple of methods, actually quite a few. A default constructor with no parameters, a constructor with a radius passed, a constructor with even more information passed, like the color of the circle, whether it's filled, and the radius. We have some getters and setters for our circle to give us our various pieces of information. And then we also have a subclass that's a rectangle. And in a rectangle, we've added a width and height as our measurement. data variables that we want to keep track of in this class, and we have some different getters and setters available for our rectangle. Now in the PowerPoint, if you've noticed, if you click on these links, we'll show you the code. Now this code is also available to you, of course, through Revell and in your book, but this is a nice, easy way for you to be able to copy and paste the code into Eclipse or NetBeans or whatever you're working with. So in this case, they show us the geometric object class, how the data variables are declared in the class, our default constructor for a geometric object that loads up the date created based on the current date, our constructor for an object if we're being passed the information. Notice how it used the this parameter to specify the data values because it's going to be using the default constructor. We have our return color and all of our different methods that go along with our generic object class, or geometric object, sorry. Now one thing to notice is down here we have a toString method. Notice this uses this override keyword. The override keyword is saying that this method will override the system's toString method, which on default returns the system name of the class. We're going to override that and we're going to return a different value to our caller, and instead we're going to give some information on our object here, when it was created, what color it is, and whether it's filled or not. So this is our geometric object class. Now let me see if I can return back here to the PowerPoint. Now we also have an example code on the circle inheriting from that geometric object class. Let's take a look at that code. Here's our circle class. Notice it's in its own data file. We would right click in Eclipse on our source file and add a class, or we could add a class easily in NetBeans to create this new class file, circle from simple geometric object. Notice here we say that this extends the simple geometric object and that it adds the class variable private double radius. Now we have our constructors, just like we saw in our UML diagram. Then we have our getters and setters and some calculation items for our circle. Now in our print circle method, we print out some information about the circle. Okay, so lots to look at in this presentation. Now we see how our superclass or our parent class contains information that can be inherited by our child class, our subclass. So we're going to continue looking at all of this information throughout this chapter. Please spend some more time with this if you would like. Now, when we're working with a superclass, we are concerned about constructing an instance. We've got a derived class here, a child, and we would like to know, when we build an instance of this child, do we have to do something to construct it? Not really. When we construct an instance of our child class, the constructor of our parent class is going to be invoked implicitly. If we want to invoke it ourselves so that we know for sure this is happening, we can use the keyword super. Here's an example. In this case, we have created a child class, A, and it is inheriting from a superclass. So if I say I have a constructor of A that expects no parameters, that is the same as saying, hey, my constructor of A executes the constructor of my superclass. It's going to happen either way. If I run A, it's going to run its superclass's constructor. Here's another example. Here I have a constructor of A and it's expecting a parameter named D, and it's a double. That's cute. And I have some statements there. That is exactly the same as the constructor for A using the double named D, and it executes the superclass explicitly. So if I'm doing it explicitly, I am putting the keyword super to tell the compiler that I want to run the superclass constructor. Otherwise, it's going to happen implicitly anyways. So in this case, I'm doing that. Now, the keyword super refers to the superclass of the class. No matter what we're doing, we can use this keyword in two ways. We can call the superclass constructor, or we can call a method in the superclass individually. So we need to use that keyword super if we want to call the superclass constructor. So if we're wanting to call that and pass it some data and not use the default constructor that has no parameters, then we'll probably have to use the super keyword so that we can call that constructor passing some data. Here's an example. Here we have a class named faculty that's extending an employee. Oh, here's our employee. Let's look at it first. We have a class named employee that extends person. Oops, here's our person. A person class. And all we have here is a constructor. And in our constructor, when somebody constructs an instance of a person, we print out this line, one person's no-arg constructor is invoked. Now, when we create an instance of an employee, we are going to run this constructor here, public employee, and it says in this constructor, this, meaning this instance of the employee, and it's going to print out, number 2, invoked employees overloaded constructor, and to print out employees no-arg constructor is invoked. If we create an instance of faculty, we're going to print out for faculty's no-arg constructor is invoked. Because faculty extends employee, we will also print out all of this information that goes along with creating an instance of an employee. And because an employee extends a person, we're also going to print out all this information about a person. Because as we create an instance of a faculty, we have to execute the employee constructor. As we create an instance of an employee, we have to execute the person constructor. So you can try that. Here is a trace of the thing. So I create an instance of a faculty. It starts in the main method. It's inside our faculty class. Okay? So I'm creating an instance of a new faculty. That automatically is going to invoke the faculty constructor, which is going to invoke the employees no-arg constructor. And then that's going to invoke the person constructor. We're going to finally execute this print line statement on our person. Then we're going to execute the employee print line information. Finally, our faculty print line information as we return back. So that's a really good example of one for you to try so that you can see how those constructors are all executed as we create an instance of a subclass. So it really gives us a lot of power. It's a lot of the power of object-oriented programming. Here in this example, we have a class fruit, and all a fruit does when someone constructs it is prints out this line, fruit's constructor is invoked. We only have one constructor here of our fruit, and it expects a string of name. In our public class apple, we say we extend fruit, but we do not override the super constructor to pass in a string. So this code would not work properly because there is no-arg constructor for our fruit. So if we had a constructor for fruit with no arguments, then our apple class would be able to use that no-argument constructor to create an instance of an apple, and everything would be good in the world. But since the only constructor we have for our fruit expects a string, we have problems in paradise. We cannot create an instance of our apple. Now, whenever we're working with a subclass, remember some rules. We inherit from a superclass, but we can also add some new properties and methods, and we can override the methods of the superclass. This is where a lot of power comes from. So, for example, I have a print circle method in the circle class, and I would like to change it. I could write it as the circle is created on our super get date created and the radius is. Now, this is referring back to the beginning of the presentation where we had the object class and we overrode that object class with our circle class. So in our circle class, we had this print circle method where we just output this information about our circle. Now, if we decided that we didn't want to have that method, what we could do is just override the toString method. Remember, our geometric object class was already overriding the system toString method. It's a default method on every object. So we can add in some information to override the toString. And what we're going to do here is we're going to create a method, public string toString, in our circle class. And in that method, we're going to return the value of our superclasses toString output. So all of the output that our generic object class returns, plus the information we want to add about a circle. So our radius is whatever our radius is. So this was overriding that toString method that we have in our generic object class. So we're saying, hey, I'm not only going to do what the generic object says, my super.toString, I want to add some more to it. We can only override a method if it's public. So we've got to make sure that we don't have it listed as private inside its class, or we won't be able to override it. Now, a static method can also be inherited, but it cannot be overridden. So if we have a static method in our superclass and it's redefined in a subclass, the method defined in the superclass is hidden, so we wouldn't have access to that method by using the super keyword to get to that method. So we have to be careful of that. Now, another concept in object-oriented programming, there are some things that are very similar. Overriding involves creating a method in a child class that is the same name as the method in the parent class. And in this case, the child class is overriding that method in the parent class. We also have the ability to do overloading. And overloading is where we have a method, and in this method we have different characteristics. So we might have this method defined twice. So in our example here, we have the method p, and in this case right here, it expects a double, and it prints out that double variable. Over here, it expects an integer, and it prints out that integer. So what we can do is create some different overriding here. Let's see what we've got. Oh, this one, I see. Hang on, back up this train. Here we have class B, and we're overriding the P method. So we're saying that in class B, I have this method named P. Class A inherits from class B, and it overrides this print method named P. Okay. So it's the same, it expects the same data to be passed to it. In this example, things are a little different. Let's talk about that. Sorry, we have class B again, and it has a method named P that expects a double, and it prints out a message about that double multiplied by 2. Now in class A, we extend or inherit from class B, and we also have the same method, but in our class A, we are creating a different data type parameter value. We say we want an integer to be passed, and instead of doing this calculation, we're going to print out this information. In this case, we're overloading this method by saying that I want you to run this P method if somebody's passing in an integer. Run this one. If somebody's passing in a double, run this one. So in our example up here, if somebody calls a.p with a number 10, we're going to run this instance down here, this overloaded instance that expects an integer. But if they execute the method p on a using the parameter 10.0, that's a double value, then we're going to execute this method here because it expects a double. So overriding is where we have the same method name in our child class, and we can do different things. Overloading is where we have the same method name, but we have a different parameter list, a different data value, so that we can specify the same method name with multiple different parameter types. Both of these methods allow us to save on coding and reuse our code and make it more flexible. Every class in Java is descended from the object class. So if no inheritance is specified when a class is defined, the superclass is the class object. So we are basically implying that when we don't put the extends. And the object class is the class that we're inheriting the toString method from when we're overriding that. So whenever we want to do that, the toString method returns a string representation of the object, as I said. So whenever we specify that we want to run a toString, we can use the system default, but it's going to display something not very meaningful, like the name of the class and some sort of numeric or hex parameter about where this is in memory, so it's not very helpful. So we like to override the toString method so that it returns a digestible string representation of the object, something meaningful about our object. So we saw earlier that they were overriding the toString and returning information about the circle or about the object. Here again, our geometric object is enhanced to give us a little bit more information on overriding and overloading, and you can run this again from the presentation if you like. Very helpful. A class always defines a type. A type defined by a subclass is called a subtype, and a type defined by its superclass is called a supertype. Therefore, you could say that circle is a subtype of geometric object, and geometric object is a supertype for circle. So again, superclass, subclass, supertype, subtype, lots of different terms for the same thing. But polymorphism means that we can refer to our objects one from another, and we can reuse our code in ways that makes it more flexible for us. In this example, we're showing again about the graduate student extending from everybody, and in this case, we've just created a better output using a toString. So in our basic main, the first thing we do is create a graduate student. Our graduate student class extends our student class. Our student class extends our person class. Our person class extends the object class and overrides the toString method. So our person returns a string person. Now our student overrides the toString method and returns a string student. And finally, when we create an instance of our M object, we're printing out the toString for that information. See if we can run this. Oh darn, I was hoping I knew better. But you can again copy this code into Eclipse and get it going. I don't want to take forever on a video because I know it's quite long. But do try it so that you can see again how those constructors are executing one another to create instances of the superclass for each subclass. Now dynamic binding is what allows us to do that. This is where we can create instances of objects by using the Java virtual machine, the Java runtime, and we're going to be able to override all of our different methods, and Java is going to figure out which one to run based on the last class that has been put in place. So, you know, if class 99 overrides toString, and in class 99 we call the toString, that's where it's going to be executed. So a lot of very intense information going on with dynamic binding, deciding which method to bind to run at a certain time in your application execution. Again, the Java virtual machine dynamically binds these things at runtime. That's why we can look at the method signature. One method uses an integer one method of the same name uses a double. We're going to look at that signature to decide which version of that method to bind to your application at runtime. So all of these different things about your method signature are going to be determining which method gets bound at runtime. So a lot going on there by the Java Virtual Machine. Some generic programming here talking about allowing methods to be used generically for a wide range of object arguments. This is known as generic programming. So if a method's parameter type is a superclass or another object, you can pass an object to the method of any of the parameter subclasses. So in this case, we have our object M, and we've passed into it an object X, and no matter what we do here with our method, we're going to output the print string method of that object. So for example, if we invoke method M with a new graduate student, we would be printing out X for a new graduate student. So we would see, person, student, all that information. So be sure to try this application. Again, this is a huge, powerful capability of Java where we can use an object as a parameter to pass into another object. If we're trying to keep track of our different objects, sometimes we need to do casting, and casting allows us to convert an object of one class type to another. So this can be useful. We've seen it when we wanted to cast an integer as a double. We were able to do that to create some information early on in our programming experience. In this case here, we're saying I want to create an object named O, and it's going to be an instance of a new student. Now I can call, again, my previous M method to print out or run the toString method, and it's going to know that this object is a student, and so it'll run the toString method for the student. Lots of power. This is implicit casting, because since this class that we're working on here is already a student, we are able to do this implicit casting. It gives us a huge amount of power. Now, if we want to assign an object reference O to a variable of the student type using this type of terminology here, student B equals O, we would get a compiler error. Why? Because a student object is always an instance of an object, but an object is not necessarily an instance of a student. So even though we know that O is really a student object, for example in this case, the compiler doesn't. So we sometimes have to tell the compiler that O is a student object, and we can do that by using explicit casting. Again, this is similar to what we did earlier. So here we're saying, hey, object O is a student, cast it as such, and set it into this new student object named B. So casting, again, just says, hey, this object can be used as this certain data type. When we create a class, we're basically creating a new Java data type, and that data type can be used in any way that we could use one of the Java data types that were given to us at the beginning of our learning. So here we're saying that we can also cast from superclass to our subclass. We have a value X. We can make it an apple, or we can make it an orange. We could have trouble, so try some different things. Now, we can also use the instance of operator to test whether an object is an instance of a certain class. So in this example, we're using an if statement to say, is my object an instance of a circle? If it is, then I could get circular type information from that object. This can be very helpful if we've created an array, for example, of our objects, and we want to know as we search through our array, is this an instance of a student or a faculty or one of those different types of subclasses involved in our student structure. To understand casting, an apple is a fruit, so you can always safely assign an instance of apple to a variable for fruit. However, all of the fruit are not necessarily apples, so you have to use explicit casting to assign an instance of fruit to a variable of apple. There's an example here of a casting demo, and this talks about our geometric object so that you can see that we can use it as a circle and a rectangle, and how we can determine which is which as we're using our different objects. Now we can use the equals method to compare contents of two objects. Realize we can't necessarily do that with a basic value variable type, but we can use our object class as an example. Let's say we create a method called equals. It takes an object in. What we do is we check to see if the current object is equal to this object. For example, the equals method is overridden in the circle class. Here we say, I create the equals method. It's overriding the default system object equals method, and my object is going to be referred to as O within my method. Now I'm going to say in my method, if O is an instance of a circle, then I want to return the radius of my circle. Otherwise, I'm not going to return anything. Seems like they should be setting that as an integer or something, but we'll let you guys decide about that. All right. The equal comparison operator is used for comparing two primitive data type values or determining whether two objects have the same reference. The equals method is intended to test whether two objects have the same contents, provided that the method is modified in the defining class of the object. So the equal operator is stronger than the equals method. But sometimes you just can't use a standard if statement, so you can use the equals method. It gives you a huge amount of power. Please do some testing with it, as with all of the other items in this chapter. You can create an instance of the system ArrayList class. Because the system array is fixed in size, the ArrayList class gives you much more capabilities. You can create an unlimited number of objects. The ArrayList implements many different methods for you. You can do a .add to add an item to the ArrayList. You can specify the index location of an item you want to add. You can clear your ArrayList. You can see if it contains something, doing a search. You can get some information from the index. Many, many, many different methods here that we can run on an instance of the object ArrayList class. So I can create a new ArrayList. It's known as a generic class with a generic type E. So we'll talk about that in Java 2. But you can specify a concrete type to replace E when creating an ArrayList. So if I wanted a list of strings, for example, I could say I want to create an ArrayList of strings, and I'm going to call it cities. This is going to be a new ArrayList. Whenever I do that, I now have the ability to use all of the methods that come along with the ArrayList class to add to my array. Let's look at the example here. In this example, they've created a tester class with a main, and it creates an ArrayList of strings called cities. It adds some cities to the list. Notice how it uses the .add method. It prints out some information using some other methods like the .size method of the ArrayList. It checks to see if certain values are located in the list. Gives us a lot of capabilities. So notice that we can say .contains instead of coding that search algorithm that we were looking at the video for in our last chapter. So the ArrayList gives us a lot of capabilities that are really, really handy to use. Some differences and similarities when we're creating an array. We specify the information using this format. When we're creating an ArrayList, we have a little bit more things that we have to specify. Our generic value in this case is a string. We could have the word integer in there. We could create this ArrayList of many different types. When we're accessing an element, we use the name of our array with the index location in a standard array. In an ArrayList, we use the name of the list and then the .get method, and we pass it a value of an index as a parameter in parentheses if we want to get a specific value. We can set a specific value, again passing an integer as the array location and the value we want to have placed into our list. If we were using a standard array, we would just say the array name with the index value equals this value. So notice there are some definite differences, but a lot more capabilities with an array list. Of course, a simple array is more efficient memory-wise, but an array list gives us added functionality. So there's always a trade-off. We can convert things back and forth from array list to arrays. We can find out what the max and minimum values are in an array list. We can do a shuffle on an array list, which is very handy. And lastly, in our chapter, we have the concept of a stack. A stack is the type of an array that is first in, last out, or how should I say, last in, first out, LIFO. So it's kind of like a stack of plates. I put a stack of plates on the table. The first one in, I cannot get to that one until I take the other ones off the stack. So the last one I put on the stack is going to be the first one out. And this is another animation from the Liang website, and it shows us how a stack works. This is a special kind of data structure array that we might need to implement. This example gives us an example implementation of a stack. Whenever we add values to a stack, we pop them on. Oops, I'm sorry, I said that backwards. That removes an element from the stack. Push adds an element to the top. So you can try the stack method there in a class and get some experience working with that. Lastly, we want to talk a little bit about a different modifier. We've seen public and private. We also now should add protected to our list of modifiers. If we use the protected modifier, we are saying that anything in this package can use this method or class. So we're basically saying that now all of a sudden the package does matter. So anything can be accessed by any class in the same package or its subclasses, even if the subclasses are in a different package. So if we have a class that's public, but some of the methods within that class are protected, we could have a different package inheriting from that class. They would then be able to access those protected methods. We altogether have private, default, protected, and public. So, or we could leave it none, right, which is default. So those are our different access modifiers. Notice our visibility is increasing as we work our way across. If we set it to private, nobody can use it but our own class. If we leave it as none or default, then things within our class can get to it, I guess. If we say protected, then things within the same package or children can access these methods or classes. And if we say public, it's open. Summary. Again, a little bit more information for you. A subclass can override a protected method in its superclass and change its visibility to public. However, a subclass cannot weaken the accessibility of a method defined in the superclass. So if it's defined as public in the superclass, it must be defined as public in the subclass. So we can't really make it tighter. So the modifiers used on classes and class members, except that the final modifier can be also used on local variables in a method. A final local variable is a constant inside of a method. So if we don't want to allow any further change on a variable within a method, we can make it final when we override. So we can still use that keyword. Here is an example. We have a final class math. We can't extend that. If we have a variable named pi, that is basically a constant. It's final. I can't change it. And if I mark a method as final, it cannot be overridden by subclasses. So that's the final one. We're not going to let anybody else have another word. We got the final word. And that's it for Chapter 11. Thank you. I hope you like working with polymorphism. It gives you an amazing amount of capabilities. Please do some testing with the sample code and get as much information out of the content as you possibly can. Have a great